Please take note that in the previous diagrams you saw that the output and the collector symbols were separated. This was done to show you how they are organized and work together in the transistor. From here forward, we've simplified the transistor symbol to only show the output arm and just mention the collector so you'll remember it's still there. If you recall, the NOT gate is one of the most basic because there is only one input source and the logic of the gate is simple. It negates or inverts the input truth value. Once again, notice how a transistor also shares the same basic logic as a NOT gate. Using this first example, hopefully you have already made the connection that the filled output symbol means this circuit has an output truth value of 1, which correlates with an original input value of 0. Because the switch is off or left in an open position, this also means that an electrical potential cannot be generated and our voltage between the collector and the output arm is equal. If we then look at the opposite case, where the switch is on or in the closed position and the current is flowing, we can see once again that the final output is 0 because there is a measurable voltage difference between the collector and the output. The logic and truth table for a new type of gate that you haven't seen before, called a NOT AND gate, or NAND gate for short, is outlined here using the transistor symbols. Why is it called the NOT AND gate? The vocabulary definition of NOT AND essentially means the opposite of AND. Likewise, if you look at the truth table, it is exactly the inversion or opposite of the values seen in the AND gate truth table. You can also see the basic logic symbol for the NAND gate at the bottom. Notice that it is a modified form of the AND gate symbol, where there is an additional small circle. When we look at how the gate is organized, we see that it is similar to the AND and the OR gates, in that a NAND gate has 2 independent input variables that allows up to 4 different starting combinations. Once again, hopefully you've already made the connection that the closed circles in this first illustration means that the starting value for both input A and B is 1. Knowing the logic of the transistor is an inverter, we can see that both of these would give 0, so it's no problem to determine the total output as 0. If we think about what this means for each of the transistors, the switches are on and the gates are closed, and the current is flowing throughout. Now let's look at the next example. In this case, one of the switches is open, but the other is closed. When we apply the transistor logic and we invert the truth values, we get one of each. So how do we know what is the final output at the end? It's easiest to once again envision how the information is flowing in the circuit. We can see in the bottom transistor with the B input, there is a closed circuit with a flowing current to the ground and to the transistor with the A input. Unfortunately, this is where the current stops, because the A input is telling us that the gate or switch is open and no current can flow. Accordingly, the voltage between the output and the collector should be equal, and the final truth value is 1. In our third example, we have the opposite case to the last one, where we still have opposing input values, but this time we have a connection between the output and collector, but not to the ground, which means that there isn't an electrical potential established, and this is why the output value for the overall circuit is 1. You should use this last example as an opportunity to test yourself to see if you fully understand the overall logic for how we can link individual transistors together to make a single type of gate with an overall logic to it. Now that you've seen how the NOT AND gate is constructed using transistor logic, it is a little easier to illustrate how the AND gate would be constructed using transistors. Recall the AND gate, its truth table, and the basic logic symbol here. If we use transistors to construct a system that has the overall logic that we would find in an AND gate, that is now illustrated here. What you might immediately notice is there are elements to this diagram that look very similar to the NAND gate in the previous slide. What you haven't seen before now is a gate that is constructed with 2 individual parts, where there is actually an output of one part, like the illustration now outlined, but it serves as the input for a second part, now shown outlined. It is this processing of the second part that will determine the overall final output. I suggest you refer back to the previous slide as needed to determine the overall output from the first part of the diagram. Using the first input value shown here, we can see that the first output would be a 0, which means that the input information to the second part is to keep the switch off or open. In this case, there is no current flowing into the transistor in the second part, which keeps the voltage equal between the collector and output. This situation leads us to that final output of 1. If we were to use the basic symbols of circuitry rather than the transistors we use in electronics, we could express this same illustration with the diagram now shown here. Hopefully, this example for the AND gate logic allows you to see more fully how circuitry is a universal way for processing information, and there are a number of ways in which the language can be symbolized and written. You should use this last example as an opportunity to test yourself to see if you fully understand the overall concepts for how we are able to link individual transistors together to make a single type of gate with a specific type of logic. One row of the truth table has already been provided. Be prepared to discuss this particular example when we meet in person as a class. For your reference, I've summarized the basic gate logic table and the associated symbols for the different types of gates we have reviewed in this lecture series in this slide. In the next video of this series, we will see how these same principles are used throughout the information system we are mainly interested in this module, the cell.